this last webinar of 2020. We are delighted today to welcome Professor Mathias Fink, who is going to talk on wave control for wireless communications, from time reversal to reconfigurable intelligent metasurfaces, and this is a joint talk with Professor Geoffroy Lerosey. Professor?
Thank you. Thank you, everybody. It's nice to give the last talk in 2020. 2020 is a very difficult year for all of us, and without wireless communication, it will be a full nightmare. But because of wireless communication, I can talk to you, and you can see my slide and even some movie. And I want to tell you the story that we have pushed in our lab since nearly more than 10 years about wireless communication. How to improve wireless communication in complex medium like a city or a building. And I will speak first of what we have done on time reversal that give rise now to what is called massive MIMO. And after I will show you that all this idea can be made on another way. If instead of using many antennas, you use the intelligent metasurface. And I will try to explain you the different steps and how all this is somewhere related to a nice concept of diffraction theory and of holographic point of view of wave propagation. First of all, if you speak of microwave or radio wave, you know that the propagation of this wave can be very simple when there is no obstacle. But if you have an antenna sending a message through a city, you will have a very complex medium with a lot of scattering, reflection, and multiple scattering and multiple reflection. This is not only for city, but inside a building, you have many obstacles, you have people that move, and that make a complex configuration. This is also the case of a forest. The wave field that an antenna produces in this kind of environment is the sum of many scattered waves, and it can have a very random pattern with some nodes and antinodes, and if you are in a bad location, no signal. In optics, we know also the same kind of problem when you look how a coherent light beam goes through a diffusive medium made of many scatters. Here I use a laser beam, it's green light, it goes through milk, and if you look on a screen, how is the wave pattern? In fact, it can be like this, except here it is red color and not green color, and all of you know that when you send at one frequency a coherent beam through a diffusive medium, the wave lost completely its coherence and it becomes really an incoherent wave field. And if you look, for example, the intensity, it is a random sum of many scattered waves at each point, and it has this speckle noise pattern. And when you see this, which is typically what you receive through a diffusive medium, if you look on the screen what you receive, you see that there is a coherence length. It is a distance between two statistically independent points. And you see also that if you change the color of your light, after some frequency change, there will be a completely different pattern. And you see that when you have a complex medium, if you want to understand what happened to a wave, you have to define what is the coherence length of a wave going through this medium and what is the coherence frequency that give you, after how much change of frequency, you have a completely different pattern. This is true in a multiple scattering medium, but what I say is also true in a cavity. And for example, a room is usually a kind of cavity, leaky cavity, and the room usually is not a regular cavity. It is more what is called a chaotic cavity or a random cavity. And you have the same problem. If you have an antenna sending one monochromatic frequency, if you look what is the field in the room, there will be a place where you have node or antinode, and you have a speckled pattern, but it is here in 2 dimensions, and you have some location where the field is good, where the field is not good. And this is typically of what happened in a chaotic cavity. And you can also define a coherence length, but the coherence length can be very small in a room, because typically, if when you send a wave, you have reflection on the boundary that randomize all the plane waves that are created by the boundary, it is like you focus everywhere from all directions, and the coherence length of such a field in such a chaotic room can be just of the order of half the wavelength, which means you have a very small coherence length here. And now, if you are changing a little bit the frequency, you have also a change of the pattern, and you have also a concept of coherence frequency, which is related to the spectral distance between 2 eigenmodes of a cavity. And this is mathematically relatively analog to what happened in multiple scattering medium, but here it is multiple reflection. These are 2 cases where a wave is strongly distorted by the medium where it propagates. Now, if you want to control the field in such a medium, that is to say, if you want to have a smart antenna, instead of using just one antenna, you can use an array of antenna, and it can be like this, or like this, or like this, or like this. And it's a complex set of antenna. All of them can be controlled to transmit a different signal from each of them with a different amplitude and phase, for example, in transmit. It can also work in receive. And when you have a kind of set of antenna like this, you can define what we call a transmission matrix through a complex medium. For example, if the transmitter are many elements that you have at your disposal, you have many antenna here. And now, if you want to send a signal to many receiver, you have many antenna here. And between all this antenna and this antenna, if the medium is not changing, just a snapshot, you can measure what is called the transmission matrix. Each element sends a monochromatic signal, and you measure here on each antenna as a receiver the phase and amplitude of this monochromatic signal. And you can acquire a transfer matrix for each frequency of your spectrum. And this will depend, of course, on the complexity of your medium. And in fact, the medium is not only in between the two, but it can be around the two if it is a cavity. And knowing the transfer matrix of a medium is very important to know how much information you can send in this kind of medium. Now, the basic idea, when you have one antenna, here I just put one antenna in point R1, and I just mimic a complex medium, like here, milk for, if I work for optical wave, but it can be a forest of obstacle. If I have one antenna located at position R1, and if this antenna sends just a monochromatic signal, I can look what I have at one receiver at position R. And I can define one element of the transfer matrix between R1 and R. And I can have a different set of antenna at different position. These are transmitter, R1, R2, R3. And I can define many elements of the transmission matrix. This matrix has spatial reciprocity if the medium is not changing. That is to say, what you receive from R1 to R is the same if R sends something to R1. Now, if you just send signal with one antenna at frequency omega, if you look on a plane, what is the modulus of the field that you receive on a plane, or the intensity? You will have this speckled figure, which is well known. This comes from position R1. Now, if you have a second position, a second antenna, if the two antennas are at a distance which is bigger than the spatial coherence of your field, you can guarantee that you have a new speckle which is completely incoherent with the first one. The amplitude has nothing to do and the phase has nothing to do. If you have an antenna at position R3, it will be another speckle. Now, if all these three antennas send together the same phase and the same amplitude at frequency omega, you will receive the sum of all these. This is the modulus of the field, but the sum take care of the phase. And here, on one point, there will be no focusing. It will be just a mixture of all this. Now, if you look what you have at one point, it is the summation of all the amplitude that you have here with the phase that are random because R1 and R2 and R3 are uncorrelated. And in this case, you can add many antenna. You will have always a field. And if you are happy, you are at a good point to receive a message. But if you are not happy, you don't receive too much. This is what we call spatial diversity. You work at one frequency, monochromatic signal, and you have spatial diversity, different antenna that see the same target from different point of view. And you have this. Now, if you want to have a strong signal here, you have to send from these three antenna, not identical signal with the same phase, but you have to take into account the transfer matrix that you have between Ri and R, and you have to phase conjugate it here. Now, if each antenna send exactly the reverse of the response between R and R1 and R and R2, but when I say the reverse, it means the phase conjugated signal. The phase is exactly the reverse of the phase that you have in the first step. And if you put the good amplitude, now if you look, if the three antenna, if you look what you have here, you have always the sum of the three pattern, but now because you have put the phase all equal, because you have do phase conjugation here, you will see that now you have a signal that become to increase at this position. And in fact, what you have done was to compensate all the phase between each point emitter and the receiver, taking into account multipath. And now you begin to build something that becomes strong. And if you have many antenna, each of them separated from a distance larger than the coherence length of your field, all of them will add coherently. And if you look what you have at another point, it will add incoherently, and you will begin to focus. This is called phase conjugation. But here it needs spatial diversity, many antenna to focus. Now let us look what you have if you have only one antenna, but now if you use broadband signal. If you imagine that you have one antenna at position R2, but now you send a signal with frequency omega 1, you will have a pattern in this plane, which is a speckle pattern with some amplitude and phase. And now if you send another color from the same antenna, a red color, you will have a new pattern, but all the signal will oscillate at frequency omega 2. And if you send now another color, green, you will have another speckle pattern. You can notice that the size of the speckle point depends on the frequency you have, that is to say on the wavelength, and it depends also on the aperture of your diffusing medium. The size is the same size that what will give a length of dimension of this dimension focusing on this point. But now, when just a point sends a signal, imagine that instead of sending free frequency, you send a broadband spectrum, and for example, you send a short pulse. The short pulse is nothing else than the summation of different frequency. What is interesting in a short pulse is that all this frequency has a phase which is identical. There is no phase shift between each frequency. All of them are added together at this time. And if you have this, now if you look what you receive at point R, you will receive color blue, color red, color green, each of them will oscillate at this frequency, and you will receive a summation of all the speckles of different color. But now this summation, because the phase that you have for omega-3, omega-2, omega-1 are random, if the two colors are uncorrelated in frequency, they are random, and you will add you will have a summation of all this complex number, which has all random phase multiplied by this. And this gives you dispersion. And you will have a signal which is spread in time. And this is reverberation, diffusive regime. And you don't like this because when you send a short pulse, here a guy receives a long pulse, which is very random aspect. Now, this is when you have one antenna. And we call this frequency diversity. You have many uncorrelated frequency, and the sum of all these give you a very random noise signal. But now you can decide, if you have only one antenna, can I send a signal which is not a short pulse, but which is something better to learn how to focus on this point? And you have just to take the signal that we have observed here, time reverse this signal, and now you put the time reverse signal as a source of this point. If you put the time reverse of this signal, it is exactly like you do the phase conjugation of all your impulse response at frequency omega-1, omega-2, omega-3. Phase conjugation and time reversal are related through a Fourier transform. And now you will send all this signal, but you have exactly compensated the difference in phase for the different color. If you send this now from one antenna, you will receive here a signal that at magic time, I call this time T0, will be exactly the summation of all my signal, but without any dephasing between them. And it will be a recompressed field, and you call this focusing in time. You will receive at one magic time all the signal that add together, but here it is different frequency. And you see that even if you have only one antenna, if this antenna sends a broadband signal with a very complex time series, here you will have suddenly a focusing at one point and at one time. And if you compare at the same time what you receive at another point, the phase for each component of the spectrum are no more in phase, and they don't add. And you see that you begin to create a focusing, even if you have one omnidirectional antenna. But what you are doing is that you use the multiple scattering medium to enhance your aperture, and you focus on a spot like if the medium become a lens, and the medium is the lens when you play time reversal. But to do this, you need to have very large bandwidth to have many uncorrelated frequency in your spectrum. And this is a way to focus a message from one point to another point with a good signal to noise. Now, this is time reversal for broadband signal, but you see that we define what we call spatial diversity, and we define frequency diversity. And if you have a complex medium, you can have many spatial diversity and many frequency diversity, and you can mix them. You can decide to have a set of antenna, each of them sending many frequency. And you have at your disposal many spatial temporal degree of freedom that depend of your bandwidth compared to the spectral correlation of your medium and the coherence length of your medium. And you can play with them. In fact, we begin to play with them very long time ago in our lab, in 95, but with ultrasound. It was a time where this was impossible to do with microwave. And at this time, we were playing ultrasound. We have a set of antenna for ultrasound, which are piezoelectric transducer, and we were sending a signal through a very complex medium made of 1,000 steel rods. This is a medium that completely destructs the coherence of your beam. And we were sending just a short pulse. We were listening long coda that we receive on each transducer, because you have a lot of frequency medium with your bandwidth, and you receive all these signals, which are very long coda. Now, if you time reverse this signal, and if you resend them from the same antenna, and if you look what come back through the same medium, you can try to look how you focus and how you recompress in time and in space your energy. And you have a concept of focal length, a concept of aperture size, and you have a very nice experiment. If you can send this very long coda for many antenna. Here there was 40 antenna or something like this. And if you look what come here, it is a very short signal, like 1 bit of information. And if you look what is the size of a focal spot, it is a very thin focal spot, which is much thinner than the same focal spot that you will obtain if you have not a random medium. If you have nothing, just free space, like free propagation in space, you will focus on a very large size focal spot, lambda, the wavelength, f, focal length divided by the aperture. But now, if you have introduced your random medium, now you have a very thin focal spot. Okay, you will say, okay, it's nice, you completely compensated. But now what is interesting is that if I want to send information here from a set of antenna, I can play with this because I know that if I have a random medium, the medium becomes a lens. If I do phase conjugation at many frequency, I can play with this. And we have done this a long time ago. We have taken this kind of medium and we decide to send a lot of information to different antenna. And at the same time, we want to send information to one antenna here, another antenna here, another antenna here. And we were introducing the random medium or just free space. And the big difference when you have a random medium is that we can learn from all these 5 antenna what is received. And if we time reverse, it will refocus on 5 different beams. If you have not this medium between the two, if you try to focus, you can focus, but you have a very large focal spot that make that each antenna receive the same focal spot. And you cannot have different channel of information in your medium. And when you were playing with this, we found that the number of information we can send to these 5 antenna was much higher when we introduce this random medium that in free space. And we can play with what is called Shannon capacity. You know that people call MIMO a system when you have many antenna to transmit and many to receive. If you have only one antenna to transmit and one to receive, like this old stuff, Shannon has tried to understand, depending on the signal to noise you have on the receiver, what is the capacity you can have. That is to say, what is the maximum rate of information that you can transfer per frequency. And the capacity depends on the signal to noise that you have on your receiver from this very well-known formula. And now, this is when one source sends something to a receiver. If you are very far, the signal loses amplitude and the signal to noise becomes bad. And you know all this. Now, if instead of having one source and one receiver, you have a set of source and a set of receiver, and now if you have a complex medium, the Shannon capacity formula can be generalized. And it was done by a guy whose name was Mustakas. And now you found that the Shannon capacity that you have that tell you how many information you can send from here to here depend always of the log of something, where the signal to noise that you have on each antenna is important. But now you have something interesting. You see that your transfer matrix appears here, and it appears as the product of H by H DAG. H is the transmission matrix between this set of antenna and this set of antenna. If you send some signal here, you receive H, what you send. Now, if you time reverse what you receive here and you send it back, you send H DAG. And now if you look this HDAG, you see that it appears in your Shannon capacity. And you see that here appears something which is the determinant of HDAG. And if you look this, and if you know that H is a matrix, and if you look the singular value decomposition of this matrix, it will have a certain number of singular values, and the singular value you have are called sigma. I hope this will disappear, Okay, and the Shannon capacity tell you that in presence of a complex medium, if you have a set of antenna, the maximum of information that you can transfer depends of sigma of the value of your singular value of this matrix. And as the number of singular value increase, you can have a better Shannon capacity. And the best is when all the singular value are equal. But if you send a signal in a medium which is free space, in our ultrasonic experiment, you have 40 antenna, and you can have 40 singular value if there is 40 receiver. But in our experiment, in free space, we have only 6 singular value. That is tell you that you can have only 6 independent channel of information. But now when you introduce a random medium, you see that suddenly through a diffusive medium, you have more singular value. You have 34 singular value. That is to say, you can have more independent channel to send information. It is like you can say you have more focal spot that spread along all this antenna. The focal spots are smaller and smaller, and you can send more information. This gives you much more information, but this is not perfect because the best will be if all the singular value has the same value to make this maximize. But this is an improvement in communication through a complex medium. Now, all this can be done with electromagnetic wave. We have done this. And later, people begin to be interested by this, but now to play with massive MIMO. The problem is that massive MIMO is very nice, but you need many active antenna. And usually you work with a limited bandwidth that don't give you many different frequency in your spectrum, which are uncorrelated. But you can play with this, and massive MIMO is a technique that is used a lot for 5G. But in massive MIMO, your problem is that you have not always in front of you a complex medium, a random medium, which is quite interesting to send more information. You have a medium which is defined by the city, by the street, and you cannot do too much, and you play with this, and this is 5G. Now, we were interested 8 years ago. I was not happy with my telephone in Brittany that don't receive a signal. And I was thinking, I have not massive MIMO. It was not 5G, it was 4G, but I have a signal which is very small on my telephone. And I was thinking, can I improve things by putting a kind of mirror in my room in Brittany and changing the shape of a mirror? It's a passive device, not an active device. And coming from this idea, I want to explain you the main idea. Imagine that between a point A and a point B, you want to maximize the information content that you want to send to B. This tells you that you want to have a signal to noise on point B when point A sends a small amount of energy. You know, if you are in an open space, when point A sends energy, the energy will diverge and you will lose signal in 1/r² as you leave point A to point B. But imagine that you are in a room which is an ellipsoidal room. And if you put point A just at one foci of your ellipsoidal room and you send a signal, and if you just put a receiver on point B, you will have exactly the same phase for all the signal. You will have a direct signal plus all the signal that go all around and focus here. And now you will have a very good signal. You can have this in the French in the Parisian metro, when you speak from one position to another position in the metro, the sound is very well focused. But usually you are in an environment which is not an ellipsoidal environment, and A and B are not at the foci. Now you have any kind of room, point A sends signal, point B receive. Perhaps you are an antinode, perhaps at a node, you don't know. Now you can decide to change the boundary of your room, and you can decide to put on your boundary which is controllable, but a very simple boundary in our ID. It was just a small boundary where you divide it in cells of lambda over 2 size, lambda over 2 square, and each of these boundary can be in 2 states. It can be or conductive or isolator, or if you want, it can be a PEC or magnetic boundary, Dirichlet or Neumann boundary. And if you play this, it will be a boundary that when a signal comes, can reflect the signal or in phase or out of phase. And you ask, can I make a tunable boundary to make that all this signal come back in phase at point B? And the idea that is behind this is the following idea. Imagine that you have a complex room, that between a point A and a point B, there is a very bad communication because you have obstacles. Point A can be outside of the room, and you have a window that make a small part of the energy come. Imagine that you want to transform your wall to improve the communication between A and B. Imagine first that point A emits a signal at one frequency. This is narrowband. Here, you have an element of the transfer matrix, and you have for each point Ri, each small cell is at a location Ri, you have a complex number with amplitude and phase. And you record this if you have a receiver that can record the amplitude and phase. Now imagine that point B emits also something, and you can record on this same transfer element. And you have in your memory the signature of point A and of point B. Now, and the signature is just an amplitude depending of Ri and the phase. The same for B. Now, imagine that, sorry, I will try to move this. Imagine that now you have a mirror, which is an ideal mirror where you can control the reflectivity, not a two-state reflectivity, but a perfect reflectivity. I can have any reflectivity with any amplitude. It tells me that the reflectivity is 1 or between 0 and 1, and with any phase, that is to say, it is a phasor. Now, imagine that my mirror here, I put the reflectivity of my mirror. Sorry, I have a small problem. Okay. Point A, I've emitted a signal, I record it, and now imagine that I create a reflectivity of my mirror, which is exactly the phase conjugated of what is coming from A. In this case, my mirror becomes a phase conjugated mirror, and if A sends a signal on it, everything comes back on A. This is phase conjugation. Now, imagine that point B, you record the signal from income point B, and now you create a mirror with phase conjugation from B. This will be the phase conjugated mirror to B, and what you send on B, come back on B. But it is not very interesting. It is not what we want to do. What we want to do is to connect A and B. And now the mirror we have to build here must have the reflectivity, which is the product of the two phase conjugated mirror, the one coming from A and the one coming from B. Because if I am creating here just a mirror with this phase, with this mirror reflectivity, it is like it compensates perfectly the phase coming from A to Ri and the phase coming from Ri to B. That is to say, all the signal coming from A going through the mirror, if it has this reflectivity, will add all the signal coming from each element will add together. But now it is only a double phase conjugated mirror to put in perfect connection. But you have also some signal going from A to B. If there are obstacles, you have nothing, but if there is some small part that can go through over multipath, you have what people call line of sight communication, or sometimes other kind of communication that don't go through the mirror. And this part also gives you a signal. And now, if you want that this plus the direct path are in phase, you have to measure the difference in phase between the two and to compensate here for all the elements. And in this case, if you are playing with this, now you optimize the communication between A and B, and you have a very good signal to noise in your communication. Now, this is very nice, and somewhere this idea of making a mirror, which is the product of two-phase conjugated mirror, is related to the concept of holography. Not exactly holography, but it is not very far. Perhaps you remember that when you have two sources, A and B, sending two waves at frequency omega, if you look on the mirror plane, the intensity of the field you receive, if the two sources are coherent, same frequency, you have an intensity pattern that appears here, which is the interference of the two fields. And you obtain an intensity that depends on the intensity of each beam plus a crossing term. And this crossing term is the product of A and B, but cosine of the phase coming from A minus the phase coming from B. And if there is a dephasing between B and A, you take this into account. And you know that an hologram somewhere is a transmission, is a transmittance, usually that is related to this part. And this is called an amplitude hologram. And you can also build what is called a phase hologram to connect A and B. And here, we create a mirror. It's not a transmittance, and the mirror is nearly like an hologram, but like a phase hologram, but here there is a plus instead of a minus. It is a reverse phase hologram. And if you can measure the field, play, you will make a perfect connection. Now, it is not so easy to measure the field on each element and to play with this, and I will come back on this just after. Now, two things which are important. If you have to build a perfect reverse phase hologram or a perfect mirror, it's needed that you control exactly on each element the phase of the reflector and the amplitude. It is too complicated. You can do just a phase-only mirror. You will forget the amplitude, and you will just reverse the phase, which is not bad. And you can just build a phase-only mirror, which is one nice step. And now you can also do a second step. Instead of reversing exactly the phase with perfect quantification of the phase, you can do what is called a binary phase mirror. And a binary phase mirror is very simple. It will give you or a reflection with phase 0 or with phase pi. It is a two-state mirror, which is very easy to implement and to play with it if you need to build complex algorithm. Why focusing with a two-state phase law is nice? Because when you want to focus, usually you want to put a perfect phase law. And when you do what is called a Fresnel lens, for example, it's perfect phasing to focus on point A. And if you build a reflector which has this perfect reflecting law, it will refocus perfectly on point A, and the phase law is this. This is the phase law which is perfect. But now, if you want to replace this perfect phase mirror by a mirror which is where the phase sampling is strong, you will have only, for example, 4 phase or 2 phase. You can ask how it works. And in fact, there is a nice theorem that tell you that when you look this function exponential g phi, it is a periodic function of phi. with period 2 pi. And if you replace this function by just phase sampling, you can have a periodic function, and you can do a Fourier transform of this periodic function, and you can find a very nice theorem that tells you that if you replace exponential g phi, which is a perfect phase law, by a discrete approximation of the phase law, it is like when you do a Fourier series, when you compare one sinusoidal wave with one rectangular periodic wave. And you have a decomposition of your field. If you use just a p-state phase law, in fact, you replace the perfect phase law that you want to focus by a set of converging mirrors, one having the same focal length, but you have other converging mirror with smaller focal, and you have also diverging mirror. And when you sample the phase law, instead of creating a perfect phase law, the first element that creates a parasitic wave is this diverging mirror plus the converging mirror. And depending on how big is P, the number of phases, you have an idea of how much energy you put in another parasitic wave that you call, which is a divergent wave. And if you play with this, for example, with 4 states, when you build a phase mirror like this, it is exactly like you have a perfect phase mirror plus parasitic mirror that send a signal here, here, here. A diverging wave will give you diverging wave and noise. And you can make just, you can look how much energy you have when you replace this that give you a big peak by a 2-state phase, for example. You will have always this big peak, except the peak is a little bit smaller. There is this 2 over pi function that tell you it is not as strong, but you have also parasitic wave that give you some noise. And the first parasitic wave is a diverging wave that give you energy here. And if you compare what you have here with the energy coming from the parasitic wave, it is like a noise, and you can have an idea with this homothetic factor of what is this noise. And you can compare this peak to this level that give you the side lobe. And if you have a good size mirror, in fact, the ratio between the main lobe and the side lobe, even if you replace this by a 2-state phase, which is not very complicated to do, you have a very good focusing, except you have some more signal. But you don't care too much. What is important is to focus. And okay, this can give you parasitic wave, but if you play with this, it can be interesting. And now, because of this, we decide to build this kind of metasurface that are small reflector, every lambda over 2. Each of them can be just a reflector with phase 0 or phase pi. To do this, it's very simple. You take a perfect mirror, you send an incident wave, and you put a resonator. And if a resonator is just at the frequency you send, you know that there is a phase shift of pi over 2. It's come back on the boundary, it's come back a second time, and now you will call this state 0. Your signal come back with the same phase, 2 times pi over 2 and pi. Now, if you just change a little bit the resonance frequency of your element, now you will have pi, and this will be the second state. And to obtain this, it is very simple. You have just to put small resonator, and you have just to put a parasitic resonator, and with a diode, you can put this in contact or not in contact. And if it is in contact, it will shift a little bit the frequency, and you will have a 2-state rule. And we build this, and we control that on some bandwidth, we can make this 2-state. And 2-state, it's very simple, because it's robust. It is not like you want to control perfectly the phase. And now we can play with this. We can put an antenna in another room, send a signal. You have a poor signal here, and you have your wall, and you begin to play with this. Of course, how you play with this. You have two ways. Or you can measure the amplitude and the phase coming from this antenna and this antenna. And if you know this, you can build this hologram. But it is not very simple to do this double phase conjugated mirror measuring the field. Now you can do this without measuring anything, just by using an iterative algorithm. And if you are in a room which is relatively complex, you know that the spatial correlation of the field has a length which is lambda over 2. That tell you that the field you measure in one point and in another point are not too much correlated. And this tell you that you can begin with your mirror in some state where you have +1, -1 somewhere. And you look on your telephone, what is the level of the signal? And you change 1 pixel. If you see that the telephone has a better signal, you say it's good. And after you go to another pixel and you try to look how it changed. And after you do iteration. And if there are some correlation between your signal, you can do a certain number of iterations. But things can be quite nice. Fabrice Lemoult here is playing with this. You have a surface, you have an antenna. You found an hologram that corresponds to focus on this point here. Now you move this to go in a place where you have no signal. The system learn. Here it is slow because it was going through, but the signal, the system learn how to focus quickly on this antenna, and it can be very fast. And we found a way by using only a 2-state. If you have to work with P state, it is much difficult to find an optimization. 2-state, it's very digital oriented, digital 2-state. And you play with this. Now, we decide with Geoffroy some years ago to create a startup. And we were a little bit enthusiastic, and we create a startup. The name is not well written. It is Greener Wave, because we can make wave green. Why? Because the idea was the following. You don't need to send a lot of energy from your base station. You can send not too much energy, but if in the room close to you, there are these boundaries that are, that change, you change the environment of your room to make that the signal you receive from one antenna in the room or one antenna very far go through the good path to focus on your antenna. And we were very excited by the idea. But when we published our first paper in 2014, nobody were interested by this. And when we discuss with communication company, they tell us, forget, it's not interesting. We don't see why this metasurface can play a role. Until the beginning, January 2020, nobody was looking for this. And suddenly, people discover that this exists. And suddenly, there was a lot of people beginning to work on this, and they call this RIS, Reconfigurable Intelligent Surface, or LIS, Large Intelligent Surface. How to put this surface everywhere in the city to make that you don't need to send too much energy from the base antenna and to have a good level of signal close to you. And when we were in this configuration with Greener Wave, we found that nobody was interested by developing this concept of reconfigurable intelligent surface, and we decided to use our surface to create other applications. And we begin by doing very high frequency Metasurface to do 5G antenna. We begin to build radar with this kind, and this replaced many antenna by just a Metasurface that changes configuration. And we demonstrate something, and this was the beginning where people were beginning to be interested. We say the following. We say that channel capacity, or the capacity that you have, if you have a defined environment, it is given by this. And the number of channel that you can have is given by your environment. Is it a very complex environment or not a complex environment? And we decide to put area of your environment, which is the room where you are, this metasurface. And we decide to look how many singular value we have when you have many antennas that emit and many that receive, not only one that emit and one that receive, but now we were playing MIMO, like in 5G. And we say how MIMO can work if you add a metasurface that you can change. If you focus badly here, it means that your focal spot is very big. And in fact, in this case, if you are in a free space, you have only one channel, and the channel capacity in MIMO is very poor because there is only one channel. If you have a perfectly random medium here, it's not bad. You increase your aperture because of the medium, but the spectrum of your singular value has this kind of form, and it gives you many channels, but these channels are not optimal on the point of view of intensity. Some are strong, some are weak. And you can do what is called water filling. It's a technique to reinforce some channel to have more energy. But we can also decide to maximize the chaoticity of your room to make that by changing the boundary, you create independent channels that all have the same singular value. And we decide to find a maximization process to optimize the Shannon capacity in a given environment. The given environment was my desktop, my room where I am. And we put this boundary and we begin to change the configuration of the boundary to make that it was with a 4x4 antenna. And we begin by having bad channel where the singular value has an amplitude which is not good. And we found a configuration that maximize all of them to have at the end all the channel which are all orthogonal. And we maximize a kind of entropy on the singular value. And we found that we can maximize the information by changing the environment. Our first paper was here. When we published this paper, it was in 2019. People begin to look, and we published another paper in 2020, I think at the beginning, or no, 2019, where we say an idea whose time has come. And since this time, there was, I will say, this number of paper on. And now people are asking the following: you have your base station with some antenna. People propose now to put on some building close to this kind of big metasurface to send in some direction of some street. And of course, you will add this kind in inside room to play with it. But you have a huge problem. You have M-based antenna. You have your reconfigurable intelligent surface, which has a lot of pixels, and you have many users. And now you have to find how all this can be optimized. And all these 300 papers are on mathematical optimization of this kind of configuration. And this is not for 5G. 5G just learn now to focus wave with many antenna on some spot or with a small number of antenna, but it is an active focusing. Now in 6G, people think that this reconfigurable intelligent surface can be of interest. The energy consumption is very small, just small diode. And in fact, they allow you to have very big solid angle to refocus on all your device. And it will be a way to use the less energy from your base station to have a more signal on each user. And now we are not only, there are many papers on this and many people in China especially that work on this and in the United States. And there was a group that recently built a very big metasurface with 3,000 elements, I think, or something like this. But each of them are two states. One is reflecting state, one is absorbing. And it is a kind of mirror, but you lose half the signal. And they propose a huge panel like this. And the cost of this panel is very small, in fact. And this is what is interesting. And it can be panels which are not rigid. It can be also changing. Now, Greenaway is playing on this. But now, because I am at a webinar of people that love acoustics, can you do the same, not only for microwave, but for acoustical wave? And we decide to push with Guangkong Ma in Hong Kong, and I work with him there and with Professor Ping Cheng to try to build reconfigurable metasurface, but for sound wave. But here, the first one that we built was a transmit lens. It is not a mirror, it's a transmitter. It is a transmittance where you have many elements, here 200 elements, and each of these elements are in fact a small membrane. And a wave coming here will be transmitted through this, and it depends on the frequency resonance of your transmitter. And now we can change this very simply. We put a platelet, which is magnetic on each membrane. And if you just applied the magnetic field on each element, now you rigidify each membrane. And by doing this, we were able to create elements that can transmit a wave or in phase or out of phase. And by playing on this, it was a beautiful experiment done by Guangkong Ma. We were able in a room where you have a source and a receiver, not only to maximize the signal, but to minimize, because with sound wave, it's better to minimize sometimes. If you have a machine creating some frequency, you want to have zero here, and you can find a configuration that destructs things here. And we have begun to play with this. It was in 2018 that we published this. But this is relatively limited because this is more in transmit, not in reflection. And the problem you have with sound is very broadband. If you want to speak in a room and play with this kind of wall, you have to be able to create metasurface that control the sound in phase for each frequency of your spectrum, each frequency decorrelation of your room. That is to say, this is very nice for narrowband signal, this concept, but for very broadband signal like sound, it's not enough. And we are looking in the lab with Fabrice Lemoult how to build reconfigurable metasurface for sound, which are broadband. For wireless, we have not this problem because when we work at 2.4 gigahertz, the bandwidth is 50 megahertz or 70 megahertz, even with the beginning of 5G. And we are relatively narrowband, and our metasurface are narrowband. Now, how to build a mirror which is very broadband, and we are working on this, and it is a nice topic of interest. Well, I think I am. It was perhaps a little bit long, but I stop here. These are relatively classical techniques. I don't speak of how a time material that changes property in time very quickly can be used for this. Here, we change the property of our material slowly. It's just reconfigurable, not ultra-fast change. I stop here. Thank you.
Thank you very much, Professor Fink. It's perfect. It's exactly 1 hour. Perfect timing. Perfect. So now we have our questions and answers. So Please, people, come forward with your questions.